Hey everyone, here is Andrea, and in this video I'm going to show you how to use the Savitzky-Golay filter for smoothing your data. As I already told you, this is a filter and it's used for smoothing the data, and so let's say eliminating the noise or useless or meaningless fluctuations that you can have in your when you have some data points and you want to analyze them. It happens quite a lot of times that you have data and they are too noisy to be analyzed as in the way that they present themselves. So the first thing that you want to do when you have this noisy data set is to smooth the signals in order to get a more understandable signal that can be further processed. So I will start by importing all the libraries that I will use in this example. So first I will use NumPy. Then we can import matplotlib.pyplot as plt. Perfect. Since I can import it later, and then we're gonna import the Savitzky-Golay filter. That is a function which is in the SciPy signal library. So from scipy.signal import and it's called savgo underscore filter. Perfect. So with NumPy we're gonna generate an array or a couple of arrays. With matplotlib we're gonna plot our arrays, and also with the Savitzky-Golay filter we're gonna smooth our data and then plot them. Perfect. So I would start by generating a random signal which has some noise in order to have some data to process. So let's say generating let's see, a noisy signal again. Signal, generating a noisy signal. So to do that, first of all I'm gonna create an X array, and I will call it X. I will use the function of NumPy linspace, and I'll start from 0, and then let's say I'll go until 2 times let's say numpy.py, which is pi, the function for generating the number pi, and then so from 0 to 2 pi, and I will subdivide this interval in 100 smaller intervals. Then I will generate the Y array. Again, we'll use NumPy and some functions of NumPy this time. So we'll use the sine function, sine of x, plus let's see, numpy.cosine of x. Perfect. Plus let's generate some noise. I usually use the function random.random, which generates a random integer number, and I have to give it as an input the maximum value. So from it will choose a random number from 0 to the number that I specify here in the brackets, and I will use 100. So perfect. This X and Y will describe our noisy signal. Okay, I can plot them in order to show you the result at this stage. So plotting as usual. Okay, to plot usual things, fig equal plt dot figure, the axis ax equal fig dot subplots. Perfect. And then let's see, I can just ax dot plot x and y plt dot show. Perfect, just to see if it's working correctly. Okay, this is our signal. Oh, so I can move it here, sorry. This is our signal. Perfect. So I'll just delete this since we're not using it anymore. So at this point, sorry, we have our X, we have our original, let's say our original data set, which is given by these two arrays. In order to apply the Savitzky-Golay filter to the Y array, it's sufficient to apply this function here. So let me just applying the Savitzky-Golay filter. Perfect. I'll call the resulting Y array, so the smoothed array, Y underscore filtered, and this will be equal to savgo. Here's the function savgo filter. So this function accepts as input 3 mandatory parameters, which are the array that we want to analyze. In this case, it's Y. The so-called window length, which is basically the size of the window, so basically the number of points that will be used by the filter to calculate the fit. And this is the important thing is that this should be a positive odd number. I will start and then I will explain you why with 99. And of course the window length should be lower than the length of your array. And then the third mandatory parameter is the order of the polynomial functions that the filter will use to fit your dataset. And I will go with 3, a order 3 polynomial function. So perfect. And at this point, basically, with this calling here, we get our filtered array. Here I can show you, this is in the official documentation. You have a lot more optional parameters. You can also specify the value of the derivative, or I don't know, the mode with which the function is going to calculate the fit, and so on. But yeah, the mandatory parameter are the first 3 parameters, and these are the ones that I'm going to show you in this example. So as I told you, here we already got our filtered signal. So let's plot again the result. So here I can then do this ax.plot. So this is the original dataset, and in order to distinguish it from the other, I will plot it by specifying, which is like this is for obtaining dotted and a mixed line with dot and lines and segments basically. And then I'll plot also the filtered signal. So the X array will be the same, and then the Y will be the Y filtered array. I will specify the color. I will go with green. Perfect, and should be all, I think. plt.show. Let's see. Perfect. So the green curve here is our smoothed signal, while the blue one here with the stars is our original dataset. As you can see, I mean the smoothing of the smoothing is really high. Basically, we smoothed the original signal quite a lot, I would say. The fit is pretty good actually, but I mean this could be one case in which you are not interested in getting all this noise here, but sometimes it could be that you are interested in some of this noise. I mean, this is up to you or up to the signal that you want to process actually. But yeah, let's see how the filtered signal change as we change the window length, so the second parameter here. And I'll do that by creating a slider button in order to be able to change in real time the window length and to see the updated result in the Matplotlib window. So to do that, the first thing that I'm going to do is to make interactive this plot here, so putting a comma. Then I also want to move the plot a little bit higher in order to create some space for the slider button. I would go with 0.5, 0.25 should be fine. Let's give me some space here. Okay, so let's start by defining the slider. Okay, so to define the slider, first of all we need to import, also the library that contains the slider, which is the Matplotlib widget library. So from matplotlib.widgets import slider. Perfect. Now I'm going to create the slider on the Matplotlib figure. So what I'm going to do here is I will call it ax_slide, and it's equal to plt.axis. So I'm creating the axis between which I'm going to define my slider button. So I'm going to give some input numbers, and then I'm gonna explain you if you don't know if you still don't know them, what they actually represent. Just a moment. 0.65 and 0.03. Perfect. So basically these four numbers represents, I can type it here, the X position of the slider, the Y position of the slider in the same order, and the width of the slider, and also the height. Perfect. So if I show you now what I've just created, this is the result. I've just created the axes which are responsible for the slider button. Okay. Now I have to define the properties of the slider. Properties of the slider. To do that, I will call the property, the property that I want to include and I want to change is the window length. I will call it win length, and this will be equal to slider, which is the function. I have to type in the axis to which it is referred, to ax slide. What I have when I want, the label of the slider, and it's window length. Perfect. And then I will specify these other parameters, val_min, which is the minimum value. I will type 5 because the window length should be at least higher than the polynomial order. This is a rule for the Savitzky-Golay filter. The maximum value, so it's val_max, and I will type 99. The initial value, again 99, because here I was starting with 99, so I want here also the slider to start with 99, and also the step, val step. So since the slider, the window length should be a positive odd number, the val step should be 2. In order to avoid obtaining window lengths of equal to even numbers. Okay, so now what I have to do is to create a function, and within this function I will try to update the value of the window length and also to update my plot. So creating the updating function. Perfect. I will call it update, and this function will take as input a value. I can define this variable current value, which basically get the value of the window length, the actual value of the window length, and of course it get it in as an integer. So when length dot val, with this attribute here I'm getting the value of the window length. Then I'm going to create the new y array, the new y filtered, and I just call it new underscore y, and this is simple because I have to reapply the Savitzky-Golay filter again to the y array, which is our initial data set that we want to smooth. Now for giving the window length will be represented by current v, and then the order is always 3. We don't want to change that. Perfect. What we have to do now, we have to set this as the new value. So set y data, and so basically we're going to change the value of the y array in the plot P here, and we're going to set this equal to new y. Perfect. And then at this point we have to redraw the figure in the Matplotlib window, and this is easily done by this command here, canvas.draw. Perfect, and I can just leave a comment here, redraw the figure. Perfect. So this is the function that will update our plot every time we change the value of the window length. In order to tell the script to call this function every time we change the value of the window length, we have to specify this command here. So win length dot onChange update, which is the name of the function, and then we have the plt.show. So this basically means that every time the value of the variable win length, which is the window length, which is the slider that we just defined, is changing, this command here calls the function update, which gets the value of the slider within the slider, which is window length. It reapplies the Savitzky-Golay filter with the current value of the window length, and then it set the y data on the plot equal to the new filtered signal and redraw the figure. So I can just specify again with another comment, when to call the update function. Perfect. I think we should be mostly done. Let me try to compile and to run the script. It seems to work. So basically here's our initial fit. So we have our noisy signal and our smoothed dataset. Now if I place my cursor here and I change the window length, you can see that the smooth signal is slowly changing, and as I decrease the window length, I will take into account much more of the noise of the original data set. I can just go quickly to lower numbers. As you can see here, we have a noisy, we are including in our analysis a little bit of the original noise, and when we get to very low value, we are basically taking into account all the noise of the original signal. So this is up to you. I mean, it depends on the use that you want to do with your the application that you have to use for which you have to use your filter, because sometimes some type of noises are meaningful for your analysis. Sometimes you just want to get rid of all the noise within your signal. So depending on your needs, actually, you have to tune the window length and also, of course, the order of the polynomial function in order to get the best fit and also to avoid unnecessary and meaningless noises. So that's it. Here it's working again. Perfect. I think that it's all for this video. Hope you like it, and see you in the next one.